Okay, so we're going to look at lecture 6 on this vector algebra section of the module. We're going to be looking down here at the vector equation of a line and the triple vector product, which we saw in the last lecture. And we're going to look at, as usual, in the Cartesian form as well as the vector form, and look at some examples. So we can look at the cross product. Here's some diagrams. You'll recognise all of these. This is the cross product. This is in terms of vectors. There's the normal vector, which is at right angles to the vector containing A and B. Either of it's a right hand rule. A cross B we can write down in terms of the determinant form. You must be able to expand that. We can calculate moments of a force, and we can calculate the area of a parallelogram, all using the cross product or the vector product. Let's have a look at the triple vector product now. Now we'll see A cross B and then cross that with C is equal to B times A dot C. A dot C produces a scalar, so this will be B times a scalar minus A times a scalar from B dot C. There's a definition of the vector triple product. We can rearrange that. And it turns out that A cross B dot C equals the volume divided by three vectors, A, B and C. Okay, we call that a parallel pipe. We can work out the volume. So another geometric calculation we can do with vectors, which is quite handy. We can expand the triple vector product. If we can write it out in those three different ways, then we can expand it in the determinant format. We write the components of A, B and C into a 3x3 matrix, a determinant of that 3x3 matrix, and the resulting vector is our solution. And in this case, it's the volume of, it can be interpreted as the volume of this parallel piped shape, or a three-dimensional parallelogram if you like. Let's look at it again, and if D equals B cross C, we get this vector with the three components D1, D2, D3. If A dot B cross C equals A dot D, then it would be that. Simply expanding the components. Expand further. We can see how we can write the same thing out as the determinant. Let's have a look at this 2D problem. We've got 2 points, A and B. How far apart are they? Well, we can do this simply by geometry, certainly in 2 dimensions. The distance is 2 minus 1, 1, 1 minus 3 minus 2, square root and those, sum them and square them, sum, take the square root. So AB in vector form is 1, 2, 1 minus 2. We can call that OB minus OA in vector form. Yep, nothing new there. Let's have a look at this in terms of how we might write a vector form of a line. So we've got 2 vectors OB and OA, and the line between B and A is minus OB OA. How far is it from A to B? How would we work this out? X distance is 1, Y distance is 2. AB is 1, 2, AB equals that. Let's see, a line through A and B with position vectors AB. A point on the line, P is a point on that line, so we've got two defined points A and B, and we've got some, let's say a 3 point that moves along, it's got vector R, it could be in any position. We define those 3 points as we have done previously, OA, OB, OP. From the diagram we know that OP equals OA plus AP. Right? We haven't defined AP, but we can write that in terms of our defined vectors A, R and A. And then we can say if T is some multiple of the distance A to B, so AP equals TAB, then we can write R equals A plus TAB. Yep. And it turns out that this is the equation of our line in vector form, because AB equals B minus A. That's our equation of a line in vector form. Actually rearrange it slightly to make it a little bit more convenient to use, but there we have an equation of a line in vector format. Quite different to y equals mx plus c, but that's the form. It's infinitely long line, so t can go to minus and plus infinity. Vector equation of a line in 3D, well, it's not going to be any different really. We just have 3 components to our vectors, R, A and B. X, Y, Z will be 1 minus T A plus TB, which can be rearranged however we want to have, like so. We can take out the X components and we see that we can write it in X components in T in terms of X component and the A components. We can similarly do the same thing for the Y and Z components. So let's have a look at the Cartesian equation of a line through A and B. In terms of our vector representation, components of a vector, then this is how we'd write our Cartesian form. Let's hope that makes sense. It seems to be an awful lot more complex than y equals mx plus c, but it turns out to be useful to when we get 3 dimensions and complex geometry that we need to add together. There just needs to be a slight caveat on your normal arithmetic. If any denominator, that's the one, the bottom number is 0, then the corresponding numerator must be assumed to be 0. We need to write that rule to avoid infinities in our calculations. Oh, here's a picture of this represented in 3D. R is x0, y0, z0 plus t, a, b, c. So there's r0, that's the point on the plane, and t can be that way or that way. So we could say that x naught is TA, y is y naught plus tb, z is z naught plus tc. Just rearranging this above equation. We can rearrange this Cartesian form into components, so we rewrite it as this vector form, or this vector form where this x, y, z is in fact a vector. And now it returns back to where we started a couple of slides ago. So let's do an example. It becomes a bit clearer when we see an example. So find the equation of a line R1 through points 0, 1, minus 2 and 3, 4, 3 in both vector and Cartesian format. So we've got this equation R equals 1 minus TA plus TB, or A equals T B minus A. So R1 equals A plus T minus T B minus A. Right. Let's put some numbers in there. It's quite straightforward to do that. So that's the equation of the line R1. Yeah. In Cartesian form, we rewrite the R1 as x, y, z. So we just rearrange this whole thing so that in the three components, so x equals 3t plus 0, y equals 3t plus 1, and z equals 5t minus 2, and rearranged into expressions of in terms of t, then we can equate all three, and there's our Cartesian form. Another example, find the equation of the line through points 1, 1, 0, 3, minus 3, minus 2, minus 7. Straightforward to write down the equation. Expand it, rearrange them all to be in terms of t, and equate them. That's a Cartesian form. Another example of equation of a line. Do R1 and R2 intersect? Well, how do we know that? Well, we've got R1 and R2. We've just calculated these using S instead of T for R2, just to differentiate them. At any point, if R1 equals R2, then the two lines intersect at one single point. This results in three equations where the x is all equal, the 1 is all equal, the z is all equal. Are there any s's and t's where these are? This can be the case. We can see that from our equations, if t equals minus 1 and s is equal to 1 into that, it gives minus 7, 7, hence the three equations are satisfied, so the lines do intersect. Substituting s or t into any of the vectors gives the point of intersection, which turns out for this one R1 equals minus 3, minus 2, 7. Find the angle between the two lines. So we know about angles. We've got through two vectors in the line. It's the component of t. we just do our dot product to find cos theta. So the angle between these two is 173 degrees. Equation of a line problem again. Determine the line that passes through the points point 0, minus 38 and is parallel to the line given by this component for Cartesian form. We've got 3 coordinates. Passes through the z plane. If it does give the coordinates of that point on a z plane. Let me just read this again, make it clear. Determine if the line that passes through the point and is parallel to this line. So we can always get a line parallel to another line and passing through a single given point. That's all doable. Determine if that line passes through the xz plane. So it only not pass through that if it's parallel to it. So essentially, we need to look at our coordinates of the equation of that line. Let's write the equation in vector form of the line. This line parallel to that is simply a scalar multiple of the vector 3, 12, minus 1, which defines the direction. Hence the equation of the new line is one that passes through that point which we were given. If it passes through the xz plane, then we must have y equals 0 at some point. Set y for 0 to solve for t. So we set y for 0, t equals 1/4. So at the point on the xz plane where this line that's parallel to the one we were given passes through 0, minus 3, 8, it has coordinates 3/4, 0, 31/4 when it passes through the xz plane. That's y, when y equals 0. So the answer is it does, and this is the coordinate. Okay, we're going to look at some examples here. This example is find the vector equation of the line joining 2 points P and Q. Pretty straightforward. This is quite a standard sort of question for equations of lines. Yeah. So we have 2 points. We need a vector that is going to be in a line joining those 2 points. So the easiest thing to do is calculate the vector between those. So it's essentially Q minus P, which gives us 639. The vector equation of the line is simply R, which is our normal position vector for any point in the line. A point and the position vector. A point being any point. So we'll use P because we know P is on the line. Minus 1, minus 2, 1, minus 1, minus 1. Minus 1, minus 2, minus 1, times by some multiplier, and we'll use T here, because we've used T quite a lot, times a vector in the line. So a vector in the line, 639. Now another vector in the line is 2, 1, 3. Why do we know that? Because it's a multiple, well, it's a fraction. Divide 6 by 3 is 2, 3 by 3 is 1, 9 by 3 is 1. So we don't need to use that 639. We can use some factor of that, some multiple of it. And we'd often do that if we wanted to simplify it, maybe put it into integers. But note the multiplier is going to be different. I've written it down as T2 here. We can also write an equation where we're using the multiplier, a new multiplier with the original vector, but we need a point in the line, and another point that we know in the line is 518. Q is 518. So any of these three are valid, and other ones are too. Say multiples of these, and well, we don't really know any other points in the line, but we could put one in if we had one. Second example here is find the vector equation of the line AB passing through the points A and B. Well, pretty much the same as the last example. AB is 2 minus 1 minus 1 minus 1, which is 0, 3 minus 2, which is 1. And then we simply write R being a point in the line times a vector in the line, which is our AB. We could also write R, and the position vector is a point in the line plus S, some different multiplier, times the position, so the vector in the line. Okay, we're going to look at a further example. Okay, so what have we got here? We've got a line passing through point A, 1 minus 1, 0, parallel to the line BC, where B and C are points on that line which have coordinates like this. So we're going to calculate a vector on BC, which will be the difference of those two, and this needs to we need to show that this passes through this line. So let's see. So we first of all calculate the vector BC, which is simply 2 minus minus 3, 1 minus 2, and 0 minus 1. Well, we've written it in with the IJK coordinate style here. So the equation is then written R equals the point A, which is 1 minus 1, 0, times by, and we're using lambda as the multiplier here, 5 minus 1 minus 1. Okay. To show that this point D is on the line, all we do is substitute in the values of our of the coordinates of D. So can it ever be equal to that for any value of lambda? So we say for x, 1 plus 5 lambda must be equal to minus 14. For y, minus 1 minus lambda is equal to 2. And for z minus lambda equals 3. Well, we can see the only value of lambda that will work for z will be lambda equals minus 3. Does it work for the other? Minus 1 minus minus 3 equals 2. 1 plus minus 15 equals minus 14. So yeah, lambda equals minus 3 works for all. So D does lie on the line. So key points here. The vector triple product is defined as A cross B dotted with C, and that gives the volume if A, B and C are three vectors defining a parallel pipe shape. You have to show that A and B and C are none of them are parallel, or that they're not all in the same plane. A, B and C are vectors, and the result is a scalar, because the last calculation we do is a scalar, a dot product, a scalar product. We can write it as the determinant form. Now here's the determinant form, so it's easier to remember. Remember to work on doing that determinant. Make sure you can do it without much thinking, but of course you're always going to have to concentrate. Simple calculations, but lots of little ones that you need to get right. You need to get the signs right, so be careful. The equation of a line in vector form, r equals a plus t b minus a, or we often rearrange it to be r equals 1 minus t a plus tb, and t goes from 0 to infinity, so r represents a vector of every point on the line. We can write this same equation in terms of Cartesian components, and we'll often write it like this, but is effectively three separate equations for x, for y and for z, but it's rearranged here, so they're all in terms of this t. The triple vector product can also be used to calculate moments of force along an arbitrary axis. This is different to about a point, where we just take moment r cross f, where r is the position vector of a point along the line where f acts, to the point where we want the moment. If we want it about a axis, well, r will be a point on the axis, and we'll multiply it with the dot product by a unit vector along the axis where we want the moments. Okay. Contents of the lectures now, of what we've done: vector equation of a line, Cartesian components, and some examples, namely moments of along a line, moments of a point. Essentially, we've done examples also of lines crossing, whether lines cross a plane, and whether lines are parallel. Okay, thank you.